Okay, let's unpack this. You've seen it everywhere, right? Tools like ChatGPT, Gemini, Claude LLM, I mean, they can write essays, explain tricky concepts, even help you code.
It's really exploded.
And think about how fast ChatGPT hitting 100 million users in just 2 months. Instagram took, what, 2.5 years for that? It's absolutely wild how quickly this stuff became part of our lives.
It really is an unprecedented speed of adoption. And for anyone encountering these powerful tools, that natural question pops up pretty fast. How does this actually work? It feels incredibly sophisticated almost.
Like magic.
Yeah, exactly. Like magic sometimes.
And that's exactly our mission today. We're taking a deep dive into the engine behind these tools, what are known as large language models, or LLMs. You shared a stack of great sources with us for this. Videos from ByteByteGo, IBM Technology, How to Fly, Matthew Berman, 3 Blue 1 Brown. Great stuff.
Yeah, some really good explainers out there.
And our goal is basically to strip away the complexity, give you a clear understanding of the fundamental ideas. You definitely don't need a computer science degree. We're just going to pull out the essential nuggets, those aha moments, so you feel like you actually get what's going on under the hood.
Mm-hmm. We want to help you understand the core mechanics without getting bogged down in, unnecessary jargon. This deep dive is really custom tailored for you. Whether you're curious for school, maybe prepping for something new, or just want to grasp this major technological shift happening all around us, we'll keep it grounded and clear.
Okay, sounds good. So let's jump right in. At the most basic level, what is an LLM?
Okay, so at its heart, an LLM is a type of sophisticated computer program called a neural network.
Okay, neural network. Heard that term. Like, inspired by the brain.
Loosely inspired, yeah.
Yeah.
Think of it as a system of interconnected calculation units, layers of them that can learn from data.
Layers of numerical processors, sort of.
Exactly. And the LLM version is trained on absolutely massive amounts of text data. We're talking soaking up information from digital books, articles, websites, conversations, even computer code.
Okay, so it reads everything.
Pretty much. Its fundamental job is to learn the statistical patterns, the grammar, the facts, the styles embedded within all that text.
And what does it do with all those learned patterns then?
It uses them to get incredibly good at one core task, predicting the next word, or actually more accurately, the next piece of a word in a sequence.
Just predicting what comes next.
That's the fundamental building block of everything it does. Just guessing what comes next over and over and over again.
Okay, so the language model part is clear, it works with text. But the large part, what does that really signify?
That large is crucial. And it refers to the scale. These models are huge, sometimes tens of gigabytes in size just for the model file itself. And the bigness is mainly measured by the number of parameters they have.
Parameters. Right, yes, that term pops up constantly. What exactly are these? Like settings?
Yeah, you can think of parameters as the adjustable knobs or weights inside this vast network. They're numerical values that the model tweaks and fine-tunes during its training process as it learns.
So more knobs means it can learn more complex stuff.
Generally, yes. More parameters can mean more complexity, more capacity to learn intricate patterns and relationships. GPT 3.5, the one that really kicked off this recent wave, had 175 billion parameters.
Billion, okay.
And GPT-4 is reported to be much, much larger, maybe holding around 1.76 trillion parameters.
Trillion. That's just a number that's hard to even picture. Wow. And you mentioned pieces of words before, not whole words.
Yes, that's right. Instead of full words, models break text down into tokens.
Tokens.
A token is roughly like 3/4 of a word, on average. For simple words like cat, it might be 1 token. But for longer words like beautifully, it might be split into bow, albally, ollie.
Huh. Why do that?
It's computationally much more efficient. Handling every possible word variation is tough, but working with these common token pieces makes the processing manageable and faster.
Got it. Tokens are the numerical Lego blocks. Parameters are the internal tuning knobs, all built on this neural network structure. I've also heard them called foundation models. Where do LLMs fit in there?
Good question. Large language models are a prime example of what's called a foundation model.
Okay.
Foundation models are basically these big systems pre-trained on huge, broad data sets so they can be adapted for many different tasks later. LLMs are the text-focused version of this, trained on a massive text foundation to be able to handle all sorts of language tasks.
And that's where we get all these different names we hear. The GPT series, Gemini, Claude, Mistral, Llama, Grok. Some are open source, some commercial, right? What's the difference?
Exactly. Open source models like Mistral or Llama are models where the core design, the sort of recipe, and maybe even the trained parameters are shared publicly.
So anyone can tinker with them.
Pretty much. Anyone can take it, study it, build upon it. Commercial models, like OpenAI's GPT series or Google's Gemini, are ones you usually access through an interface.
Hmm?
You can use the incredible dish they created, but the recipe itself, the internal workings, are kept private, like a trade secret.
Right, okay. It feels like this technology just appeared overnight, but the idea of language models actually has a history, doesn't it? It wasn't invented in 2022.
Oh, absolutely not. The concept of building systems that process and generate language isn't new at all. You can trace early ideas way back, things like ELIZA in the 1960s.
ELIZA, I remember reading about that. Super basic, right? Like finding keywords.
Very basic, yeah. Pre-programmed responses based on keywords. Then came earlier types of neural networks, like recurrent neural networks, RNNs. They could actually learn and process sequences, predict the next word.
But they weren't like this.
No, they struggled, especially with understanding context over longer pieces of text. They'd sort of forget the beginning of a sentence by the time they got to the end.
So what was the major breakthrough? What changed to get us here?
That would be the transformer architecture. It came from a landmark paper by Google researchers back in 2017. The title was Attention is All You Need.
Attention is all you need. Okay, that sounds important.
It was a complete game changer. This architecture allowed models to process text much more efficiently and, crucially, to understand the relationships between words, no matter how far apart they are in a sentence or document. That was key.
So it could pay attention to the whole context at once.
Essentially, yes.
Yeah.
And once that architecture was introduced, you saw the model sizes just start to explode. GPT-1 in 2018 had like 117 million parameters.
Which sounded big then, probably.
Right. Then GPT-2 jumped to 2.5 billion,
Mega TT.
which had made that massive leap to 175 billion. Then came ChatGPT's 3.5 version, which brought it to the mainstream. And now GPT-4 is estimated at that 1.76 trillion parameter mark.
That's scaling just in, what, 5 or 6 years? It's just astonishing.
It really is. It shows how this combination of the right architecture, the transformer,
Yeah?
and the increasing availability of vast amounts of data and massive computing power just propelled the field forward incredibly rapidly.
Okay, so we have the basics. LLMs are large neural networks trained on tons of text, fundamentally designed to predict the next token. We know a bit about their history and the transformer breakthrough. Now let's get into the really fascinating part. How does this prediction actually happen? You give it some text, your prompt, and it starts generating more. What's the process inside?
Right, the magic bit. Think about that analogy you hear sometimes, like having a script and predicting the next line.
Okay.
You read what's already there, you predict the next little bit, you add that bit to the script, and then you predict the next bit based on the now longer script. That's the core loop.
Got it. Building it piece by piece, using what it just wrote.
Exactly. So the very first step when you give a text, say your question, is tokenization.
Breaking it into those word pieces again.
Yep. It breaks down your input sentence into that sequence of numerical tokens we discussed. What is the tallest building becomes, maybe 5 or 6 token numbers.
Okay, so the computer is immediately working with numbers, not words.
Right. And then these tokens are turned into embeddings. It's a really crucial concept.
Embeddings, okay.
Every token is converted into a numerical representation. Imagine it as creating a unique numerical fingerprint, or maybe an address, for each token. This fingerprint is basically a long list of numbers, a vector.
Numerical fingerprints for words or parts of words. That sounds kind of abstract.
It can feel that way.
Yeah.
But the amazing thing is the model learns during its training to create these numerical fingerprints so that tokens with similar meanings or similar roles in language end up having similar fingerprints.
So similar words get similar numbers.
Similar lists of numbers, yeah. You can even think of these fingerprints, these vectors, as points on a vast multidimensional map. Tokens that are related end up being closer together on this map.
Like dog and puppy would be near each other.
Exactly. And even more amazing, the directions on this map can carry meaning too. This is where you get those famous examples like take the numerical fingerprint for king, subtract the fingerprint for man, and add the fingerprint for woman.
And you end up near queen?
You end up with a numerical fingerprint that is incredibly close to the one for queen. The model learns these complex relationships, these directions, just from seeing how words are used in all that training text. Comparing these numerical fingerprints mathematically tells the model how related different tokens are.
Wow. Okay, so it turns words into these numerical fingerprints, and those numbers actually capture complex relationships and meaning. That's pretty cool.
It's fundamental. But initially, These embeddings just represent the token's basic meaning, kind of out of context.
Mm.
The real leap, the thing that makes modern LLMs so powerful, comes next with that key innovation from the transformer architecture, the self-attention mechanism.
Ah, the attention is all you need part again. What does that do to the fingerprints?
This is where the model gets its deep understanding of context. The self-attention mechanism allows the model to look at all the numerical fingerprints, the embeddings, in the input sequence simultaneously.
All at once.
Yes, and then it figures out how relevant each word, each token is to every other token within that specific sentence or paragraph. It weighs the importance.
So it learns which words relate to which other words in this specific input.
Precisely. This lets it create new, refined numerical fingerprints. We can call them context-aware embeddings, where the meaning of a word is heavily influenced by the words surrounding it.
Okay, so if I say riverbank versus savings bank, the attention mechanism helps it look at the word river or savings and figure out which meaning of bank I intend.
That's exactly the idea. The attention mechanism helps it focus on the right contextual clues. Think of it like a chef reading a customer's really detailed order. They don't just look at one ingredient name in isolation. They pay attention to all the parts of the order together to understand the nuances of what the customer really wants.
That makes sense.
This self-attention is what allows LLMs to generate text that is so much more coherent and contextually appropriate than older models could ever manage.
And these context-aware fingerprints, these refined numbers, they then go through more processing, more layers.
Yes, they pass through multiple layers of the neural network. These layers perform complex mathematical calculations, essentially transforming these numerical fingerprints over and over again, guided by those billions or trillions of adjustable parameters, those knobs we talked about.
So the numbers representing the words just keep getting crunched and refined through all these stages, constantly informed by their context in the sentence.
That's the core idea. It's a lot of matrix multiplication, basically, transforming these lists of numbers. After processing the input text through all these layers and attention steps, the model reaches the point where it needs to actually generate the next token.
Right, the prediction part.
What it does is calculate a likelihood score for every single possible token it knows in its entire vocabulary.
Your every possible token. Even really weird, obscure ones, that must be thousands.
Tens of thousands, often, yes. And then a mathematical step called softmax turns these raw scores into actual probabilities that all add up neatly to 1 or 100%.
Okay, so it ends up with a list. This token has a 15% chance of being next, this one 10%, this one 0.0001%.
Exact is like that. A probability distribution over its entire vocabulary.
So how does it choose the actual next token from that huge list of probabilities?
Yeah.
Does it always just pick the one with the highest percentage? The most likely one?
Not necessarily always, and this is interesting. This step is called sampling, and it picks the next token based on those probabilities.
Yeah.
But there's a control knob here you often see in settings called temperature.
Temperature, I've seen that, like a control for creativity or randomness.
Exactly. That's a great way to put it. A low temperature setting, like close to 0, means the model is very, very likely to pick the single most probable token every single time.
So it plays it safe.
Right. This results in text that's very predictable, consistent, maybe a bit boring or repetitive sometimes.
At high temperature.
A higher temperature makes the model more willing to take chances, to occasionally pick tokens that have lower probabilities.
So low temperature is like sticking strictly to the recipe, while high temperature is like the chef improvising a bit, throwing in a surprise ingredient.
That's a perfect analogy. Higher temperature can lead to more creative, interesting, or surprising text, but it also increases the chance the model will pick a word that doesn't quite make sense, goes off track, or results in one of those confidently wrong hallucinations we hear about.
Ah, okay. So there's a trade-off. And how does it build a whole sentence or paragraph then? Does it plan it all out?
No, it doesn't plan ahead in the way a human writer might outline. It's that iterative loop we talked about. It predicts and samples the first token.
Okay.
Then it takes the original input text, PLUS, that newly generated token, treats that whole thing as the new input, and feeds it back into the model to predict the next token.
Ah, so it adds its own output back into the context for the next step.
Exactly. It repeats this process, adding one token at a time, predicting the next piece based on everything generated so far, until it reaches some stopping condition, like generating an end-of-sequence token or hitting a length limit. It's like adding one line to the script and then reading the whole updated script, including that new line, to figure out the very next line.
So it's really generating it word by word or token by token based only on what came immediately before in that sequence.
Precisely. Though it's important to know there's a limit to how much previous text the model can effectively remember or consider when predicting the next token. That limit is called its context window.
Okay, so it can't look back at an infinitely long conversation or document when deciding the next word. There's a limit to its short-term memory, so to speak.
Right. The size of that window is a technical constraint, although newer models are getting much, much better at handling longer contexts, thousands or even hundreds of thousands of tokens now.
Okay, that explains the mechanics of going from input to output. That's fascinating. But how did these models get so incredibly good at predicting text in the first place? That involves the massive training process, right?
It does. And it is a truly monumental undertaking, usually broken down into a few key stages. The first, and by far the most resource-intensive stage, is pre-training.
Pre-training, what does that involve? Sounds foundational.
It is. This is where the model is trained on those absolutely enormous data sets of text we mentioned earlier, soaking up hundreds of billions, sometimes even trillions of tokens from sources like the vastness of the internet, huge digital libraries of books, code repositories, conversational data from forums, articles, you name it.
And the quality of that data must be super important, right? If it learns from junk.
Absolutely critical. There's that old saying, garbage in, garbage out. If the training data contains biases, inaccuracies, harmful content, conspiracy theories, the model will inevitably learn and reflect those issues. Curating diverse, relatively clean, high-quality data is a massive challenge in itself.
So they just feed it this ocean of text. What's the specific goal during this pre-training stage? What's it trying to learn?
The sole goal, fundamentally, is simply to get exceptionally good at that next token prediction task across all this incredibly diverse data. That's it.
Just predict the next word millions and millions of times.
Billions and trillions of times. By constantly trying to guess the next word in countless different sentences, articles, dialogues, code snippets, the model implicitly learns grammar rules, facts about the world, different writing styles, how conversations flow, and even develops a surprising ability to perform tasks like translation or summarization, just based on the patterns it observes.
How much computing power does that take? I hear it's a lot.
The scale is honestly hard to comprehend. Training these massive models requires huge clusters of specialized computers, specifically GPUs, graphics processing units, which are really good at the parallel math needed.
Not just one computer.
Oh no. Thousands of GPUs working together, often running continuously for days, weeks, or sometimes months for the biggest models.
Yeah.
The energy consumption is enormous, and the cost easily runs into the millions, sometimes hundreds of millions of dollars, just for a single pre-training run.
Hundreds of millions. Just to train it to predict the next word really well. Wow, that really puts the large in LLM.
It certainly does. You can think of it as painstakingly tuning those trillions of parameters, those knobs, over and over again, slightly adjusting them each time to minimize the error in its next word guesses across that entire vast training data set.
And the result of all this massive effort, what do you get at the end?
You get what's called a base model.
A base model.
Okay.
And what's that like? Is it like ChatGPT?
Not quite yet. A base model is an incredibly powerful text predictor. It has absorbed a vast amount of general knowledge and learned complex linguistic patterns from the training data. It's sometimes described as a form of lossy compression of the internet. It captures the general ideas, the structures, the relationships very well, but it doesn't remember every single fact perfectly.
Lossy compression, like a blurry photo of the internet.
That's one way to think about it.
Yeah.
It remembers the gist, the patterns. This is also why these base models can sometimes generate text that looks perfectly plausible, fits the patterns it learned, but has actually completely made up those famous hallucinations. And crucially, a base model isn't automatically a helpful assistant you can chat with. It's really just a sophisticated text completion engine. It might complete your sentence, but not necessarily answer your question helpfully.
Okay, so pre-training gives you this incredibly knowledgeable pattern matching engine, but it might be unreliable, might hallucinate, and isn't really designed to be an assistant. How do they turn that into something like ChatGPT that can actually answer your questions and follow instructions?
All right, that's the next crucial stage, fine-tuning.
Fine-tuning. Okay, how is that different from pre-training? Still training, right?
Still training, yes, but very different in scale and purpose. Fine-tuning takes that pre-trained base model with all its knowledge and trains it further, but on much, much smaller and much higher quality curated data sets.
Smaller data sets. What's in them?
These data sets consist of specific examples of the kind of behavior you want the model to exhibit. Often it's things like pairs of questions and ideal answers, or instructions and desired outputs, frequently generated or verified by humans.
Ah, so it's like showing the model explicitly, hey, when someone asks this, this is a good way to respond. You're teaching it manners almost.
Exactly. You're
Yeah.
teaching it the desired style and format. The model is still using its underlying next token prediction ability, but now it's learning the specific style, format, and behavior of a helpful, harmless conversational assistant from these curated examples.
Like the example on one of the sources about training on conversations about ordering pizza to make the model good at taking pizza orders.
That's a perfect analogy. You fine-tune it on task-specific data. The great thing is, fine-tuning is significantly faster and much, much less expensive than pre-training. You're just adjusting the already knowledgeable base model, not building it from scratch.
So companies can iterate faster this way.
Precisely. This allows companies to release updated versions or specialized models more frequently. The result of fine-tuning is an assistant model, something like ChatGPT, that leverages the broad knowledge base from pre-training, but now knows how to interact with you in a conversational, instruction-following way.
Okay, that makes sense. And is that where RLHF comes in, that reinforcement learning from human feedback? Sounds complicated.
Yeah, it's another layer, yeah. RLHF is an optional but very impactful third stage, widely used for models like ChatGPT that helps refine the assistant model's behavior even further. It's particularly focused on improving helpfulness, honesty, and especially safety.
How does that work? It's not just showing it good examples anymore.
No. In RLHF, instead of just providing correct example answers, humans are shown several different responses generated by the model itself for the same prompt, the same question or instruction.
Okay, the model generates a few options.
Right. And the human workers then rank these different responses.
Yeah.
They say, this one is the best, this one is second best, this one is okay, this one is bad, based on criteria like accuracy, helpfulness, tone, and whether the response is safe or potentially harmful.
So humans are essentially voting or judging which of the model's own outputs are better.
Exactly. And it turns out it's often easier for a human to judge and rank existing responses than it is to write a perfect response from scratch themselves. Think about trying to write a perfect haiku versus just picking the best one from a list of 5 options.
Yeah, ranking seems easier.
The model then uses all this human ranking data, thousands and thousands of these comparisons, to train another model, a reward model. This reward model learns to predict which responses a human would likely prefer, which ones would get a high rank.
Okay, so it learns to predict human preference.
Yes. And then the main LLM uses this reward model as a guide. It practices generating more responses, and the reward model gives it feedback, essentially saying that response would probably get a high rank, or that one would get a low rank. Through this iterative process, the LLM adjusts its own parameters to get better and better at generating responses that maximize this predicted human preference score.
So it's learning by trial and error, guided by what humans seem to like.
And that's a good way to put it. It helps the model become more aligned with human values, more helpful in practice, and crucially, much safer by learning to avoid generating harmful or undesirable content based on that human feedback.
Wow. Okay. So pre-training builds the massive knowledge base on raw text prediction. Fine-tuning teaches it the how of being an assistant using good examples. And then RLHF refines that behavior even more, making it safer and more aligned with what humans actually prefer, using rankings that really breaks down the journey.
It's a long, complex, and very expensive journey from raw data to the polished conversational AI we interact with.
Definitely sounds like it. Now, we've talked a lot about generating text, predicting words, answering questions, but the LLMs we use today seem to be able to do so much more than just chat.
Oh, absolutely. Because they've learned so much about language structure, patterns, and the world during that intense pre-training, they turn out to be incredibly versatile. They can take a long article and give you a concise summary. They can translate between dozens of languages. They can write different kinds of creative content poems, song lyrics, marketing copy, even scripts.
Helps with coding too, right?
Hugely helpful for coding, finding bugs, writing boilerplate code, explaining code snippets, and of course, answering factual questions on a massive range of topics, drawing on that compressed knowledge of the internet.
I've also seen them do things like browse the web for current events or even create images. Is that part of the core LLM itself, or is that something extra?
That's a great question. It's not directly part of the core next token prediction engine, usually, but a huge recent advancement is teaching LLMs how to use external tools.
Tools, like giving it a hammer.
Not quite physical tools. More like giving the model access to other software or services and training it when and how to use them effectively to answer your query.
Okay, so like giving it access to a calculator if I ask a math question or a search engine.
Exactly. If you ask it for information that's very recent, something after its training data cutoff, it can learn to trigger a browsing tool to search the internet and incorporate the findings into its answer. If you ask it to analyze data or perform complex calculations it struggles with internally, it might use a code interpreter tool, like running a little Python script.
And generating images.
Same idea. If you ask it to create a picture, it might learn to call out to an image generation model like DALL-E with a well-crafted prompt based on your request and then present the resulting image to you. This ability to intelligently use tools makes them far more capable and useful problem solvers than if they only relied on their internal static training knowledge.
That makes sense. It extends their reach. And they're moving beyond just text too, right? I hear about multimodality.
Definitely. The field is rapidly moving towards multimodality. This means the models are being designed to process and generate not just text, but different types of data, different modes.
Like what?
Well, they can increasingly see images and understand their content. There are demos where you can draw a rough sketch of a website on a napkin, show it to the model via a camera, and it can generate the actual HTML and CSS code to build that website.
Seriously, that's amazing.
It's pretty incredible. They can also hear spoken language directly and speak back using realistic voices, enabling truly natural voice conversations, not just text chat. This integration of text, image, audio, and maybe even video is a major frontier.
That multimodality feels like a huge step towards more general capability.
It certainly is.
Mm.
Another really important technique you hear about quite a bit now is retrieval augmented generation, usually shortened to RAG.
RAG. What's that system doing? Sound like finding information.
It is. RAG is a clever way for LLMs to access and use information outside of their massive but potentially outdated or generic initial training data. Particularly, it lets them use information you provide.
How does that work?
If you upload a specific document, like a long PDF report, or connect the LLM to a private company database, the RAG system allows the model to first retrieve relevant snippets or chunks of information from that specific source based on your question. Then it uses those retrieved snippets, along with its general knowledge, to help formulate its response.
Ah, so it's like giving the model a specific personal library to reference for my questions, in addition to its general knowledge from the internet it was trained on.
That's a perfect analogy. It makes the responses much more grounded in the specific, up-to-date, or private information you care about, rather than just relying on potentially stale or generic knowledge it learned months or years ago during pre-training. It also helps reduce hallucinations because it's grounding the answer in provided text.
That seems really useful for businesses or specific tasks.
Hugely useful. And finally, related to this, models are becoming more customizable. You see this with features like OpenAI's GPTs in their App Store, where you can give a model specific instructions, documents, and capabilities, essentially creating a version that's tailored to be an expert in a particular narrow area you define.
So LLMs are evolving incredibly fast. From just text generators into these complex systems that can interact with the world through tools, handle different data types like images and audio, reference specific information you give them with RA, and even be customized for specific roles. That's incredibly powerful. But it also sounds like they must still have significant limitations and face major challenges. They're not perfect.
Oh, absolutely not. Far from it. Despite their impressive capabilities, current LLMs still struggle significantly with tasks that humans find relatively easy. Things like complex, multi-step mathematical reasoning, abstract, logical problem solving, or maintaining perfectly consistent arguments and factual accuracy over very long interactions.
And we keep hearing about those hallucinations where they just confidently make things up entirely.
Yes, that's a significant and persistent challenge. Because they are fundamentally trained to generate plausible-sounding sequences of tokens based on statistical patterns, they can easily generate facts, dates, names, citations, or entire events that are completely untrue, but present them with absolute confidence. They don't inherently know what's true. They know what sounds like it should be true based on the data.
That seems like a big problem if you rely on them for factual information.
It is. Verification is crucial. And then there's the issue of bias.
Right, since they learn from the internet.
Exactly. Because they are trained on massive amounts of human-generated text scraped from the internet and other sources, which inevitably contains all sorts of human biases, stereotypes, prejudices, and even toxic or harmful content present in society. The models can pick up and reflect those biases.
So they can generate biased or unfair responses?
They absolutely can. This can lead to the model generating biased, unfair, stereotypical, or even toxic content. Significant effort goes into safety fine-tuning and using techniques like RLHFs to try and mitigate this to make them safer, but it remains a really complex, ongoing battle. It's hard to completely scrub bias out.
And all this training and running these models, you said it costs a fortune earlier.
It is extremely expensive, yes. Training requires those massive, costly computing clusters and huge amounts of energy. And even just running the models to generate responses, what's called inference, uses substantial computing power and resources, especially for the largest models. This high cost is a significant barrier. Only large companies or well-funded research labs can really afford to build these state-of-the-art models from scratch.
Okay. And is it true that sometimes even the creators don't fully understand why a model gives a specific answer, the black box problem?
That's a really important point, yes. It's called the interpretability challenge. With billions or even trillions of parameters interacting in incredibly complex, nonlinear ways, it's very difficult, often practically impossible, to trace back the exact chain of reasoning or calculation that led the model to produce a specific output.
So we know what it did, but not precisely how or why.
Largely, yes. Their behavior often emerges from the complex training process, rather than following simple, understandable step-by-step logic that we can easily inspect and verify. We know how to make them better at predicting and behaving in desired ways, through more data, better training techniques, and feedback like RLHF, but we don't always have a deep understanding of how they internally represent knowledge, or why they arrived at a particular nuanced conclusion or phrasing.
That's a bit unsettling. They've also been described sometimes as System 1 thinkers. What does that mean in this context? Is that like instinctual?
Yeah, this analogy comes from psychology, distinguishing between two modes of human thought. System 1 is fast, automatic, intuitive, and relies heavily on pattern matching, like instantly recognizing a face, understanding simple sentences, or knowing 2 plus 2 before without thinking.
Okay, the quick stuff.
Right. System 2 is slow, deliberate, effortful, and involves conscious, step-by-step reasoning, like carefully working through a complex algebra problem, planning a detailed trip, or evaluating a logical argument.
So LLMs are?
Current LLMs are phenomenal System 1 thinkers. They are incredibly good at rapidly finding patterns in language and data and predicting based on those patterns. That's their core strength. But they largely lack that robust human System 2 ability for slow, deliberate, logical deduction, planning, and step-by-step reasoning. That's why they can often struggle with tasks requiring complex math, multi-step logic puzzles, or maintaining strict logical consistency. Researchers are actively exploring ways to give them more System 2-like capabilities, but it's a major challenge.
Interesting. And currently, they improve mostly by learning from humans, right? Through fine-tuning and RLHF. Does that limit how much better they can get in general language tasks? Can they surpass us if they only learn from us?
That's a really deep and debated question. Yes, for tasks like conversation, summarization, or following instructions, their improvement currently relies heavily on imitating human-generated data and incorporating human feedback. It's an open question how to make them improve beyond general human capability in these broad language domains. Unlike in games like chess or Go, where AI surpassed humans because there's a clear objective win or lose signal the AI can optimize for through self-play, there's no simple objective score for being a better conversationalist or writing a better essay beyond human judgment. How do you get them to improve beyond the human examples and preferences they learn from? It's not clear.
Lots of challenges still. And given how powerful and integrated these models are becoming, security risks must be a massive concern too.
Absolutely, a huge one. As LLMs become more integrated into operating systems, browsers, email clients, everything, new and serious security challenges emerge. One major category is jailbreak attacks.
Jailbreak, like trying to escape from the safety rules?
That's exactly the idea. It's about tricking the model into bypassing its built-in safety guidelines or instructions that were put in place during fine-tuning and RLHF.
How do people do that?
There are many creative techniques. It might involve clever prompting, like asking the model to role-play as a character who would provide dangerous or restricted information, like the infamous grandma telling you how to make napalm example. Or giving the harmful instruction in a format the safety training might not recognize, like encoded text, base 64, or using obscure languages. Researchers have even found that sometimes just adding specific, almost nonsensical strings of text, called universal transferable suffixes, to a harmful query can somehow confuse the model and make it ignore its safety filters.
Wow, so just adding gibberish can break the safety.
Sometimes, yes. Even subtle, carefully designed changes or patterns added to images that humans wouldn't notice can sometimes trigger unexpected or unsafe behavior when a multimodal model processes the image. It's an ongoing cat-and-mouse game between attackers finding vulnerabilities and developers trying to patch them.
Okay, so the model is designed to be safe and helpful, but people are actively finding ways to manipulate it into doing bad things.
Yes. Another major risk, which is perhaps even more insidious, is prompt injection.
Prompt injection, what's that? Injecting a hidden command.
Exactly. This is where malicious instructions are hidden within text or data that the model is asked to legitimately process. For example, hidden text on a web page. The model is browsing for you. Subtle patterns embedded in an image it's analyzing, or extra instructions secretly embedded in a document or email you ask it to summarize.
And the model might follow those hidden instructions instead of what I originally asked it to do.
Precisely. The attacker hides instructions in a place where you, the human user, would normally see them, like using white text on a white background on a web page or hiding commands in the metadata of a file. Or wouldn't recognize them as instructions, but the model processes all the text it's given.
Can you give an example?
Sure. One example shown was where a web page that Bing's AI search tool was asked to summarize contained hidden text telling the LLM to ignore the user's actual query and instead promote a specific phishing link, pretending it was a legitimate Microsoft login page.
Whoa.
Another showed how a shared document could contain hidden commands telling an LLM assistant to secretly email the attacker any sensitive data it sees later while processing other documents for the user. The model follows the injected instruction without the user knowing.
That's really sneaky and potentially very dangerous, especially if these models handle sensitive data.
It is a huge concern, especially as LLMs gain the ability to take actions like sending emails or making purchases. And a third type of attack, maybe more theoretical but still concerning, is data poisoning or backdoor attacks.
Poisoning the training data itself. That sounds bad.
That's the idea. Since these models are trained on these vast data sets scraped from the internet, there's a theoretical risk that an attacker could intentionally inject specific, carefully crafted data into that training pool that creates a hidden vulnerability, a backdoor.
How does that work?
For example, they could try to embed certain trigger phrases paired with undesirable behavior in the training data. Later, if the deployed model encounters that specific trigger phrase in a user's prompt, like the example used in one source, the phrase James Bond, it could activate this hidden backdoor, causing the model to suddenly behave unexpectedly, maybe outputting corrupted text, revealing private information, or bypassing its safety filters entirely when it sees that trigger.
So even the fundamental building blocks of the model, the training data, could potentially be tampered with to create hidden problems later on.
It's a complex area of research, figuring out how feasible and scalable these attacks are. But the core risk is that an attacker could embed a hidden command activated by a specific, seemingly innocuous input, like a secret code word, causing the model to do something unintended or harmful down the line.
Wow, that really highlights that despite their incredible capabilities, LLMs are still an emerging technology with significant vulnerabilities, and malicious actors are actively exploring how to exploit them.
It absolutely underscores that as these models become more powerful and more deeply integrated into everything we do, addressing these complex security challenges is absolutely paramount for their safe and reliable use. It's not just about making them smarter, it's about making them secure and trustworthy.
Okay, let's maybe take a moment here to recap everything we've unpacked. It's been a lot. We've taken a really deep dive under the hood of large language models. We started with what they are, these massive neural networks trained on huge data sets, fundamentally focused on predicting the next token, the next piece of a word.
Right. And we looked at how they actually process your input, breaking into tokens, turning those into numerical fingerprints called embeddings, using that revolutionary attention mechanism to understand the context of the whole input at once, creating context-aware representations.
Yeah, and then how those numbers go through layers and layers of calculation guided by billions or trillions of parameters, eventually leading to probabilities for every possible next token.
And how the model then samples the next token based on those probabilities, with that temperature knob controlling the level of predictability versus creativity. And crucially, how it builds responses token by token, feeding its own output back into the input for the next step.
Then we explored the immense multi-stage training process, that massive pre-training on vast internet data just to learn patterns and predict words, resulting in a knowledgeable but raw base model.
Followed by fine-tuning, using smaller, high-quality data sets of examples to teach that base model how to actually behave like a helpful conversational assistant.
And then optionally using RLHF, reinforcement learning from human feedback, where humans rank model outputs to further refine its behavior, making it safer and more aligned with what people actually prefer.
We also touched on how their capabilities are rapidly expanding beyond just simple text generation. They're learning to use external tools like search engines, code interpreters, image generators, which makes them much more powerful.
Right, becoming multimodal to handle images and audio, not just text. Using RAG, retrieval augmented generation, to reference specific documents or data you provide, making them more accurate and relevant, and even becoming customizable for specific tasks or roles.
But we also confronted the not-so-magical side. Their inherent limitations, still struggling with complex logic or math, that tendency to confidently hallucinate or make things up.
The challenge of bias picked up from flawed training data, the immense cost and hardware required to build and run them, and that interpretability problem, the difficulty in understanding exactly why they says what they say.
And finally, those significant security risks, people trying to jailbreak them, to bypass safety rules, the danger of prompt injection, hiding malicious commands in the data they process, and the potential for data poisoning creating hidden backdoors during training.
It's really clear this is a field evolving at an absolutely incredible pace. It's building on decades of research in AI and linguistics, but it feels like it was fundamentally transformed by architectures like the Transformer and just the sheer scale of data and computing power that's become available recently.
Absolutely. And hopefully understanding these fundamentals helps demystify these powerful tools you might be using or encountering every day. It gives you a clearer picture of what's actually happening behind that impressive conversational interface. It's not magic. It's complex engineering and statistics with both amazing potential and real challenges.
So here's maybe a final thought to leave you with, something to mull over as you interact with these models going forward. Given their current nature as primarily these fast, intuitive System 1 pattern matchers, but also considering their rapidly growing ability to use tools, interact across different types of data like images and sound, and the ongoing challenges in security and reliable reasoning, how might your own interaction with LLMs change in the near future? What happens as they potentially gain more capabilities that look like that slower, deliberate System 2 human reasoning, or become even more deeply embedded, almost invisibly, in the apps and services you use every single day? What does that future look and feel like to you?